Okay, as people still dial in, I might as well get started. Welcome to ICLR's hurricane forecast webinar for 2024. It's Friday, June 7th, and I'm Managing Director of ICLR, Glenn McGilvery. Last month, we brought you two talks. On May 7th, Richard Carr from the Canadian Forest Service gave the 2024 wildfire forecast. And then on May 10th, Dr. Sherry Molnar spoke about Vancouver seismic microresonation maps. Both of those video replays can be found on our YouTube channel. And we just recently surpassed 400 videos on our channel. So it's a very rich source of information. So please do check that out. And if any of your colleagues miss today, you can point that out to them and I can provide you a link if you need it. This month, we're going to bring you two talks again. So along with today's talk, next Friday, Patrick Folsey will tell us about best practices and cautionary stories about roofing and cladding. But today, we bring you Bob Robichaud of the Canadian Hurricane Center. Again, he's going to present on the 2024 North Atlantic Basin hurricane forecast. That season began just 5 days ago on June 1st. And the season is forecasted to be above normal, with the NOAA predicting between 17 and 25 named storms, of which 4 to 7 could be category 3, 4, or 5. Bob's here to tell us more, as he's done almost every year since 2010. I've been around for that whole time, and every year I think we have a few more gray hairs and a few more aches and pains. But Bob, we really thank you for your time that you give to us each year. Bob serves as a warning preparedness meteorologist at the Canadian Hurricane Center. He's been a meteorologist for almost 30 years. He was briefly a weather forecaster in the private sector, but has served in the Canadian federal government since '98. And everybody turns to him for hurricane forecasts, including our own industry, insurers, reinsurers, Cat IQ, the media, Environment and Climate Change Canada, and so on and so forth. And if I'm not mistaken, last year, I think you even dipped into the wildfire side of things, but we can maybe talk about that a bit later on. This is the agenda for the next little while. Our webinar will last about an hour. We'll see how that goes. Bob will present for about 45 minutes or so, and then I'll moderate a Q&A for the rest of that time. So please feel free to chat your questions in the Q&A box at the bottom of the screen, not the chat box, but the Q&A. And I'll pose your questions a little bit later on. This session, of course, is recorded and we'll hopefully have it up on our YouTube channel Monday or Tuesday, so keep an eye for that. And with that, I'm going to hand it over to Bob.
All right. Thank you very much, Glenn. Yeah, it's if my recollection goes is correct, it goes even farther back than 2010. I think 2007-ish is when I started doing these in person, and then we kind of switched to online way before the pandemic. But certainly we've been at this for quite some time. So I'm just gonna share my screen. And I believe I should be sharing right now. Okay, so I will assume that I'm sharing at full screen. So good day, everyone. Basically, these hurricane briefings, we've received some fairly good feedback on the structure of them. So I'm just going to kind of follow what I typically follow. And since we only deal with these types of storms over a certain part of the year, it's good to do a review of what tropical cyclones are all about, why they form, where they form, and the particular hazards that they bring. And then I'll do a quick review of what we saw last year. Last year was also an active season. And then we'll take a look at what we might expect for 2024. So the energy distribution in terms of heat is certainly, as we can all imagine, is much more pronounced near the equator and in the tropics, because those areas of the planet actually get more energy from the sun, than other areas. Certainly, much more than what would be received at the poles. So what happens is the water temperature in the ocean basins across the globe get warmer and warmer, especially during the summer seasons of both hemispheres. So you tend to get a much warmer area of water near those areas of the equator and the tropics over the course of a year. So again, that is way more than compared to what we get at the poles, and that creates an imbalance. And nature tries to counteract that imbalance in terms of heat that's stored in the ocean. The mechanism, or at least one of the mechanisms to counteract that imbalance, is the formation of tropical cyclones. So how does that occur? These as the warmer water gets in place, what happens is you have upward currents of air that take all this very moisture laden air that's near the surface, just above the ocean, and push it upwards. As that air goes upwards in the atmosphere, it cools. As it cools, the moisture that's contained in that air condenses, and then when that process occurs, heat gets released into the atmosphere. And that's the process really that takes heat from the ocean and pumps it into the atmosphere. So with everything else being equal, when you have a warmer ocean, you tend to get more of these storms developing over the course of a given year because there's more heat stored in the ocean. And that's going to be critical as we get into the forecast for this hurricane season. So the structure of these things, you get these bands. This is a cross section of a pure hurricane. You get these successive bands of heavier precipitation and then a break, heavier precipitation. And the closer you get to the center of the storm, the heavier the precipitation is going to be and the stronger the winds are going to be as well. A lot of this air, again, rises. Some of it flows out the top of the atmosphere, while some of it flows down the center. Whenever you have descending air, that air tends to dry out, and that's why the eye of a pure hurricane is often cloud free and sometimes clear right to the ocean surface. So here in kind of the more northern latitudes, at least removed from the tropics, we got a couple of different things that we have to deal with. Um, we do get some pure tropical cyclones coming our way, and this is an example of one here, where you have these bands flowing towards the center of the storm. Very well developed symmetrical storm here, which is very typical of a pure tropical cyclone. This is what's called a subtropical cyclone. This is a storm that works very much in the same process of what I just described, is taking heat from the ocean and then pumping it out to the atmosphere. That's what drives the intensity of that storm. But it didn't form as a tropical cyclone. It formed as some other non-tropical disturbance, and then it acquires tropical characteristics over time, enough so that it gets to the point where what drives the intensity is actually that warmer water. And then we have something called a post-tropical cyclone, and that's something that we get here um, um, more often than anywhere else, as a matter of fact. And that is a scenario where you have either a pure tropical cyclone or a subtropical cyclone that transforms into something from a structural perspective that looks more like what you would see with a winter storm. So at that point, once a storm is declared post-tropical, it says nothing about the strength of the storm. What it really means is that storm no longer gets its energy from the heat that's stored in the ocean. Rather, it gets its energy from temperature differences between the north and the south, or the east and the west. So different mechanisms that drive the intensity of the storm. And we can have, as we've seen over the course of just the last few years, very, very intense post-tropical storms that affect Atlantic Canada, even into Quebec and Ontario possibly as well. Because at that point, you no longer need that warm water to drive the intensity. Now, when a storm goes from tropical to post-tropical, again, it doesn't mean it's a weaker storm necessarily, but certain things happen to that storm, specifically with respect to the hazards. In terms of the wind, you can have a storm where you have very strong winds on both sides. But what often happens when a storm is either going through that transition or is finally declared post-tropical is that the storm is moving quite rapidly. So the storm speeds up. When the storm speeds up, you get a more pronounced difference between the winds on one side versus the winds on the other. Because the flow around the center of the storm is counterclockwise, and that storm is usually moving in a northerly direction or northeasterly or what have you, you will have stronger winds on the right hand side as opposed to the left hand side. You can still have damaging winds on the left, but they'll typically be stronger. Whatever they are on the left, they will be stronger on the right, much more significantly. Also, in terms of a storm that enters our latitudes, typically we see the strongest winds from those storms in the right hand rear quadrant of the storm. So if you look in the direction that the storm is going, that rear right quadrant is typically where we find the strongest winds with these storms. In terms of rainfall, something happens to the storm as well, is that it tends to dry out on the right hand side. So on the right hand side is typically where you're going to find your strongest winds, but the rain will shift over to the left-hand side of the track. And this is where we find our heaviest rainfall with one of these storms that approaches us. And because the winds are stronger on the right, that's where we'll typically find our highest surge and our largest waves as well, like we saw with Fiona a couple of years ago in Newfoundland and Labrador, in the Port aux Basques area. That was largely, there was some storm surge associated with that as well, but it was largely the waves that were the issue with Fiona in that part of Atlantic Canada. Now, you can still have some significant storm surge on the left-hand side of the track, depending on the geography, again, as we saw with Fiona a couple of years ago. So this is kind of representation of what you might typically see later in the hurricane season. Disturbance forms off the coast of Africa, becomes a tropical storm, evolves into a hurricane. These storms tend to move with the easterly trade winds, which tend to be fairly light. So these storms don't move very fast. 10, 15 kilometers an hour forward speed is typical for a storm in the tropics. But then it starts to, it can either go into the Gulf of Mexico, it could make landfall in southeastern parts of the US. And then another scenario is that it might recurve and make landfall further up the coast and potentially into Atlantic Canada or possibly even tracking offshore. When that happens, we typically see the wind field expanding. Again, the speed of the storm increases, it accelerates. The wind field gets bigger, as I mentioned, so the storm gets bigger, and then you have a very clear delineation between your heavy rain that's to the left and your strongest winds that are on the right. In terms of climatology, typically this time of year, as Glenn mentioned, the season starts on June 1st. Early storms tend to be either in the Gulf of Mexico or in along the southeast coast of the United States. That expands a little bit into July, and then once we get into August is when things really start to get going, with September being the peak month of hurricane season, and then it tends to dwindle a little bit in October and certainly in November as well. But really, as we get into you'll see here August, September, and October. that is when we get the bulk of our tropical cyclones. If you're looking at June, we get about 6% of all tropical cyclones or named storms that form in June. Goes up to 8 in July, and then in August it really kicks up there. In terms of major hurricanes, there haven't been very many in June. Even July, and then August is, especially the latter part of August is when you typically see that. And then 47% of all major hurricanes have really been in the month of September. So September is really the peak month of hurricane season. So the classification of these things, again, because these things form over the water, which is their whole purpose is to dissipate some of that energy that's in the warm water into the atmosphere. A lot of these storms, uh, um, what we've used to kind of designate these storms is satellite imagery. And this is kind of a representation of the satellite imagery from different storms. There's a very well published um, method that we use satellite imagery to come up with an estimate for the storm intensity, and that's called the Dvorak technique, based on things like the density of the overcast, the number of spiral bands going into a storm. In this case, from Franklin last year, you can see one here, another one here, another one here. All these things go into the determination of the estimate for the intensity of these storms. And these are all on what we call the Saffir-Simpson scale for hurricane intensity, which is designated by the maximum wind speed of the storm at any particular time. And again, as these storms form over the ocean, sometimes over the middle of the Atlantic, there's not a whole lot of observations out there to give us an idea. So we use satellite imagery a lot to determine the intensity of these storms. As the storms approach, they get closer. Then at that point, there can be some reconnaissance flights into the hurricanes using a couple of different types of aircraft. And then, as I mentioned, the satellite methods as well, right up until the storm either dissipates or makes landfall somewhere. So looking at last year, some of the predictions, again, the predictions from late May, from NOAA, they were calling for 12 to 17 named storms, 5 to 9 hurricanes, and 1 to 4 major hurricanes. And we actually got 20 named storms, which was a little more than what they had been predicting. And then as far as hurricanes and major hurricanes go, they were pretty much in that range. And if you recall from last year, we had two very distinct factors that influenced hurricane season that were opposing each other. One was a fairly robust El Nino, which is characterized by warm water in the Pacific Ocean. But we also had very warm water in the Atlantic Ocean as well. So at this time last year, we weren't exactly sure which of the two factors would end up playing the most significant role. And certainly we saw that although we did have an El Nino, it didn't really put a whole lot of damper on storms forming in the Atlantic, as you'll see in a minute, especially where they formed. So we still had 20 named storms last year, and again, 7 hurricanes and 3 major hurricanes. And the 3 major ones were Franklin, Idalia, and Lee, which we'll talk about in a second. So this is just an outline of hurricane season and when the storms were. We had a few early season ones, and then really most of the activity started after the middle of August and continued into pretty much most of September. And then we had a few more storms in October, none in November this year, where we did have one in November the previous year. So these are all the tracks of the different storms, and there's a couple of things here that kind of jump out at me. Obviously, it looks like that there's fairly good coverage of storms in the Atlantic um, last year. Not quite so much in the Gulf of Mexico. There were only three storms in the Gulf of Mexico. Now, mind you, one of them was Idalia, a major hurricane that made landfall in Florida. But this is fairly even the Western Caribbean. There wasn't a whole lot in here, which is fairly typical for a um, an El Nino year. So when we have an El Nino condition, which is, again is warm water in the Pacific, that causes more wind shear in the atmosphere in the Atlantic Ocean. That wind shear, that increased wind shear due to El Nino, is more pronounced in the Gulf of Mexico and Western Caribbean than it is in the central and eastern Atlantic. And we can see that quite clearly if we look at the tracks of the different storms. So El Nino did play a role in the development of storms last year, at least in part of the tropical Atlantic, but elsewhere, we did get a pretty good number of storms, and again, the total was 20 for last year. If we look at one of the things that we can look at is the amount of time that certain areas were spent under the cone of uncertainty, which is the forecasts that are issued by the National Hurricane Center in Miami. And this is a cumulative time spent within the cone. And you can see that of all of North America, Western Nova Scotia and Southern New Brunswick area spent the most time under the threat of a potential tropical cyclone, and that was mostly as a result of Lee and Philippe, which we'll look at in a second. But it's interesting that of all the areas, Gulf Coast, southeast coast of the U.S., it's up here in Canada that spent the most time within the cone of uncertainty from last year. One of the things I like to do is count the number of what we call shorties, or the storms that formed quickly but then dissipated quickly, that didn't really last that long. So we had a 7 that lasted on the order of at least 1 to 4 days. We had 6 that lasted 6 to 9 days, and we had 7, just as many long-lived storms last year as we did shorties. So again, an indication of a fairly active hurricane season. So we'll go through some of these storms. Dawn didn't really cause much in the way of impacts, but Dawn was the first hurricane of the year. It developed as a subtropical storm, and then it became tropical, and then eventually became, as I said, the first hurricane of the year. Very few people remember Dawn because, one, it stayed over the ocean. The other is because it became a hurricane the day after a major flooding event in Nova Scotia. So all the focus was on the recovery from the flooding event in Nova Scotia that occurred on July 21st. Nobody was paying attention to Dawn, but of course we were, as that storm was churning offshore. Then we had Franklin. Franklin was another interesting storm in that it caused a fair bit of anxiety here in Atlantic Canada. It actually formed as a tropical storm on August 20th, so in that latter period of the month of August. It did have some impacts in the Dominican Republic, and then after that, it intensified very rapidly as it moved northward. Now, some of the earlier models had Franklin come up towards Atlantic Canada, and that was actually fueled by some misinformation that was passed around on social media, and it caused a lot of anxiety in people who are still on the recovery from Fiona from the previous year. So having another potential significant storm system really caused a lot of anxiety when it didn't really need to, because some of these models, they are really, they're simulations of the atmosphere, and they're prone to change, especially far out ahead of time. But now they're all available on the internet, so people share these, and people don't quite know what they mean, and you end up causing a lot of stir when you don't need to. So that's an increasing problem that we're seeing here at the Canadian Hurricane Center, is battling that misinformation that's out there. And not only did it occur with Franklin, it also occurred with Lee, that we had to deal with as well. Another storm, certainly worth mentioning, is Idalia. Idalia was the costliest storm of last year. It made landfall as a Category 3. It peaked at a Category 4, but made landfall as a 3 at the end of August. Um, Peak winds here, that should be 213 kilometers an hour. Rainfall was the peak rainfall was 350 millimeters. There was a storm surge as well. Now, it did make landfall on one of the least populated areas in Florida, so that was kind of a bit of a saving grace there for them. There were 12 tornadoes reported with or being related to Idalia, 8 direct fatalities and 4 indirect. And the damage was $3.6 billion in the US as a result of Idalia. Then we had Major Hurricane Lee. Now, Lee was one of those classic storms that formed off the coast of Africa, and as a tropical wave, and then eventually became a tropical storm. And then it really, really rapidly intensified into a Category 5 hurricane, very, very rapidly. And it once it reached that Category 5 status, it slowed down. And as a hurricane slows down, it churns up the ocean. The ocean gets cooler because of that. So you can actually look at water temperature in the wake of a hurricane, and you can see the cooling that takes place behind, not because of the latent heat release process, but just because the water gets churned up and brings up cooler water from deeper in the ocean. So you can actually see that on infrared satellite imagery. So as the storm slowed down, it remained over its own wake, and then diminished in intensity somewhat before making a run at Atlantic Canada. There were actually 4 fatalities noted with Lee, and that was because of surf and um, rip currents, all in the U.S. So you can see the what we've categorized as explosive intensification. So it really intensified rapidly, which was very, very well handled by the model. So that was very well predicted. So it reached a Category 5, and then started to weaken somewhat. And then once it started to move again, and moving away from that cold water that it created, it started to re-intensify again. But it didn't re-intensify to what it was before. After a couple of days, it started to weaken again. It started that transition to post-tropical, and was declared post-tropical just prior to making landfall here in Nova Scotia, and then going up into the Bay of Fundy into New Brunswick. So again, the track areas with Lee were very, very low for a storm of this nature. Again, probably because it intensified so rapidly. The forecasts, especially the track forecasts, tend to be much better with a strong storm than kind of a wishy-washy, weaker storm. So because it was so strong, the track forecast was handled quite well. The intensity forecast, the rapid intensification, was also well handled as well. So there was a very very well handled storm from forecast perspective, and we did have impacts here in Atlantic Canada. They also had some in Maine in the U.S. as well. Most of our impacts here were on the order of result of storm surge and the waves, mostly along the Atlantic coast of Nova Scotia. So there were some docks and boardwalks that were destroyed, some debris washed on some roads, other roads that were destroyed, and maybe not to the same extent, but some of that occurred in New Brunswick as well. We did get some strong winds. Some of the stronger winds were on Grand Manan Island in New Brunswick and here in the Halifax area. There were 277 Nova Scotia, 1,000 Nova Scotia Power customers without power, and more than 90,000 in New Brunswick. So we did get some fairly strong winds. Again, this was at one point a major hurricane. It was much weaker by the time it got here, but it was still a significant storm nonetheless. We did get a little bit of flooding as well, as some areas got in excess of 100 millimeters of precipitation. Now, Philippe was a storm that occurred later in September and kind of had a very difficult forecast associated with it. It also it was predicted to become a stronger storm than it did, but it never actually reached its full potential, and it did affect Barbuda on October 2nd, and then started its slow trek northward. It probably dissipated before it reached Atlantic Canada, but there was another area of low pressure nearby, so it interacted with that, and then ended up that other system ended up tracking over western parts of the Maritimes into the New Brunswick Maine border and caused some heavy rain in some of those areas. But it wasn't as strong as Lee was just a few weeks earlier. But again, the forecasts were very challenging with this one. Again, just because the storm was so wishy-washy, and it accounted for about a quarter of all the errors in the track forecast for 2023 was this one storm, Philippe, and in some of the discussions from the National Hurricane Center bulletins, they mentioned the word uncertainty or low confidence or model spread 58 times. So that gives you an idea just how difficult this thing was to forecast. And although this is not an Atlantic storm, it certainly is worthy of a mention from 2023, and that was Major Hurricane Otis. Otis was one of these storms, late season storms in October, that ended up intensifying very, very rapidly over a short period of time, just prior to making landfall. And in discussions with the forecasters in Miami, this is kind of their worst case scenario where you go to bed at night and you have a tropical storm that's approaching. You wake up the next morning and basically you have a major hurricane at the doorstep. And this is exactly what happened there. There were very warm waters just off the coast of Acapulco, and the storm, as it was moving over that water just before making landfall, it intensified 177 kilometers per hour in that 24-hour period. So this is the satellite view at 1 a.m. Central Daylight Time on October 24th. You can see it is a tropical storm at that point. There's no well-defined eye. There's some banding to it, but overall, it doesn't appear on satellite imagery to be that strong a storm, which of course it wasn't. It was peak winds were 80 kilometers per hour. And then within 24 hours, the peak winds went to 265 kilometers per hour. Again, this is 1 a.m. Central Daylight Time on October 25th, so 24 hours from that. You can see very dense overcast around a well-defined center, just making landfall in the Acapulco area. So this is, again, their worst case scenario. And this is the kind of thing that could happen in a major populated area in the US. Very unlikely that something like this would happen here, almost impossible that something like that would happen here in Canada because the water off our coast simply is not warm enough to sustain a storm of this nature. But there's a scenario where they've taken an example from Otis where you could have this same scenario hitting Miami, for example. So these are some of the things that are that keep us forecasters up at night is this kind of scenario. So you can see here, this is the black line here is the intensity, the actual intensity of the storm. The blue lines, blue dashed lines are the forecast intensity from NHC. And it really is on that 24th of October that things really started to ramp up very, very quickly. And we saw that storm reach Category 5 status just prior to making landfall. And of course, as these storms get their energy from the warm water, as soon as it made landfall, the intensity dropped right off, like one would expect. But again, a very, very dangerous situation, and then causing 52 fatalities and an estimated 12 to 16 billion dollars in damage. And it's the costliest tropical cyclone on record for Mexico, and not only that, it's one of the costliest natural disasters of all time in Mexico, whether it's you're talking a hurricane or earthquake or whatever. So again, very, very difficult situation there with Otis from last year. So overall in the season, there were 19 fatalities, which is significant. But if you look at the fatalities from 2022, we had 303 fatalities in 2022. So much, much lower for 2023, despite it being the fourth most active hurricane season, or tied for it at least, with those 20 named storms. Over $4 billion in damages, which is again much lower than the 119 billion from 2022. But again, despite the 20 named storms, the strongest storm was Lee. So it's 2 years in a row now that the strongest storm of the Atlantic hurricane season ends up having impacts in Canada, with Fiona from last year, and then Lee this year. Mind you, it wasn't at its peak intensity, but still, we're seeing some of those stronger storms here. The costliest storm last year was $3.6 billion, and that was with Idalia. So Idalia caused the majority of the damages from last year's hurricane season. One interesting aspect I mentioned where these storms tend to form in the early part of the season. Well, in June, we had tropical storms Brett and Cindy that actually formed further out in the middle of the ocean, which is fairly rare and hadn't happened since 1997. So an interesting tidbit there from where these storms developed early in the season last year. So now it's time to refocus on this year and where things are going with the potential for storms this year. And this is a graphic that I've shown before, and I like how it depicts the relationship between wind shear in the Atlantic and the water temperature in the Atlantic. So the blue curve here is wind shear over the course of the year, and you can see in the winter time into the early summer, you have a fair amount of wind shear. Then it starts to drop off significantly as we head into the summer. And wind shear, you really can't underestimate the impact of wind shear on a tropical cyclone. When a tropical cyclone, like I showed in one of the earlier slides, they tend to be very vertical. Whenever you have wind shear, it really disrupts that development. So you tend to get much fewer storms in an area that has a lot of wind shear. The Gulf of Mexico, for example, the waters are warm there year round to sustain tropical cyclone activity. but it's the wind shear that kicks up in those winter months, and that's why we don't see storms down there at that time of the year. But as we head into the summer, that wind shear really starts to drop off, and then it reaches a low um, point in the month of August or early September before it starts to creep up again. Meanwhile, the water temperature gets warmer and warmer and warmer over the course of the summer, and it actually peaks towards the end of September. But the peak of hurricane season is right around um, right between those two peaks, the peak of the ocean temperatures in the Atlantic and the wind shear over the Atlantic in the atmosphere as well. So that peak is right around September 10th. So this is the indicators that we look for. For wind shear, we look at water temperature in the Pacific. Again, if the water temperature around the equator in the Pacific, um, off the coast of South America, is warmer than average, that's a condition we call El Nino and tends to create more wind shear in the tropical Atlantic. And then the relationship with water temperature in the Atlantic, it's much more clearer. It's the warmer the water, the more storms you're going to get. Again, everything else being equal. So we look at water temperature. We also look at heat content, the amount of heat that's stored in the ocean that's available for these storms to develop. So we're going to take a look at that now. So this is water temperature anomaly. So the departure from normal of water temperature around the globe, and you can see that for the Atlantic, just in the tropical Atlantic, this is last year. Water temperatures were quite warm. So we started off last year in the winter time with water temperatures being near average to slightly above average, but they shot up in during the summer months. So by the time we reached the peak of hurricane season, water temperatures had reached record levels in the Atlantic. And that was one of the main drivers that pushed us over the edge in terms of the number of named storms, despite the fact that we had a fairly robust El Nino, evidenced here by the warmer water in the equatorial Atlantic. So this was last year. Let's take a look at this year. This is actually today. So I'm going to go back to last year, and you can see this warm patch of water here has really moderated and has actually started to cool. There's some areas in here where the water is actually colder than average. This is sea surface temperature. However, that we know that the water below the surface is a fair bit cooler than that even. So we know there's a good supply of cool water just in the slightly deeper ocean, which is why we think this is going to really rapidly go from a warmer scenario to a colder scenario as we head into the summer. Now, if we look at the Atlantic, we have warm water from the coast of Africa all the way into the Gulf of Mexico, including the Southern Caribbean as well. Again, comparing last year to this year, very, very warm water in the Atlantic. In fact, we are still looking at record water temperature in the Atlantic, which I'll show in a second. So we'll first start in the Pacific and see where we're going with that. So again, if we look at this patch of water in the Pacific, we can see this is the area that we look for as to whether we're in an El Nino or a La Nina. Still, because of the scale of what we're talking about here, we go on the order of a 3-month period. So we're still technically in an El Nino, but we look at all the model trends, everything is trending downward in terms of the water cooling in that area. So that by the time we reach the peak of hurricane season, which is August, September, October, we are either in a neutral situation or a La Nina condition at that point. Again, El Nino is an inhibitor for hurricane activity, so it puts a damper on hurricane formation. And despite having an El Nino last year, we still ended up with with 20 named storms because the water in the Atlantic was so warm. So every model that we look at has us out of that El Nino by the peak of hurricane season. In fact, this is the official forecast from NOAA for the El Nino, La Nina, and we are 77. This was issued in May. Their update is supposed to come out next week, I believe, for June, which is going to be, I think, even higher than 77. But at the time, this was the latest official one. And they are calling for a 77% chance of being La Nina, 22% chance of being neutral, and only a 1% chance that will still be in El Nino by that time. So, overwhelming evidence that we are heading towards a La Nina. Now, let's look at sea surface temperature in the Atlantic. So, this is the average here since 1981, these gray lines here. This orange line is the sea surface temperature, again, in the North Atlantic, in the entire North Atlantic last year. So you can see just how warm the waters were in the Atlantic last year, way, way above average. In fact, it was record water temperatures for most of the summer. That continued into the winter. And once we got into January, we were still looking at record warmth water. And this is the black line here is the current water temperature. So we are above where we were last year. So that is some very concerning numbers to look at. And if we look at looking at this a slightly different way and focusing on the what we call the main development region, which is this area in here, and this is where we look at water temperatures because this is where um, these storms tend to form. Again, we're way above, we're at record heat content in the ocean. This is heat content. And we are at record levels right now. And it's just going to get warmer as the summer goes on, which is again very, very concerning. If we look at what some of the models are predicting in terms of water temperature anomaly in the Atlantic, again, this is from the ECMWF or the European modeling, and they project this to be, again, to remain very, very warm in the Atlantic and the Gulf of Mexico over the course of this summer. This is the average anomaly of sea surface temperature for August, September, and October, again, which is the peak of hurricane season. So all this to talk about some of the numbers that are out there. So there are a number of agencies that issue these, and I'll show these in a second. Some of the ones, the earlier ones that came out, Tropical Storm Risk, they issue one in December. They updated in April. Colorado State, they issue their initial outlook in early April, and they're due for an update next Tuesday, June 11th. Weatherbell is a private company. They're looking at 25 to 30. The Europeans, they are looking at 23 named storms and 13 hurricanes. NOAA, which we kind of follow what they do, and we coincide our media briefings with the release of their outlook. They're calling for 17 to 25 named storms, 8 to 14 hurricanes, which would be a lot, and 4 to 7 major hurricanes. And you can see there how that compares to the average, way, way above average. If you're wondering how these outlooks perform, so NOAA started theirs in around 2000 or so. And the top red line here is the upper part of their range, and the bottom red line is the lower end of their range, and the blue dots are the actual number of storms over that particular year. And you see that for the most part, these blue dots end up within that range. So the forecast tends to be fairly good or is very close to it. So it gives you a pretty good idea of their forecast performance, which is pretty good. Obviously, 2005, we had a very, very active year that year as well. And then 2020 was the record season for activity in the Atlantic with 30 named storms. So that is going to be something this year. The conditions are way more favorable for this year than even 2005 and 2020. So these two numbers could be challenged for sure this year. And I mentioned the different agencies that issue these things. There's a number of them. A lot of them are private weather companies, some universities, government agencies, that sort of thing. Penn State, look at Penn State. Their numbers are up to like 37 or 39 named storms, which would be completely off the charts. But this middle area in here would be normal. And then above that would be above normal. And every outlook that you can find pretty much has this hurricane season being either a record hurricane season or well above normal. Nobody has it really significantly in the normal. Nobody has it below normal because everything is pointing to a very, very active season. So the names that we're going to be using this year start with Alberto, followed by Burl and Chris, Debbie, and so on. So this is the same list that we used 6 years ago that we're using again this year. And should we run out of names, which is this year very much a possibility, it has happened before in 2005 and then 2020. But in those years, we used the Greek alphabet to name these storms. We've moved on from that, and now we have our supplemental list of names that we use should we run out of names. Again, which is if you put a lot of stock in the predictions for the number of storms, it's highly likely that we're going to end up using this list for the first time this year. And just looking at some of the responsibilities and some of the products that are available. So we here at the Canadian Hurricane Center, we focus on storms that are going to have an impact in Canada, either offshore or over land areas. We're not there to really duplicate what they do in Miami. We actually work very closely with them. We have conference calls, video conference calls, sometimes multiple times a day when a storm is approaching, just to make sure that we're all coordinated. The Hurricane Center in Miami, they're responsible for everything in the Atlantic and the Eastern Pacific. We are responsible for areas in here, within this red shaded area, which is our response zone. If a storm enters our response zone, under the World Meteorological Organization, Miami will still continue to issue products, bulletins, and track maps on a storm that will enter our response zone. We will do so as well. Usually they line up fairly well, but there's an offset of issue time. So sometimes there can be slight differences between what we have at the Canadian Hurricane Center and the Hurricane Center in Miami, but that is largely due to just an offset issue time of these different products that we have. So what we do is we just add details on impacts for Canadians in order that they are able to take measures to protect their lives and properties here in Canada when one of these storms approaches. So the number of storms that we get here compared to the total number of storms in the basin can vary from year to year. Typically, we get about 35% of the storms that form in the Atlantic find a way they track into our response zone that I mentioned earlier, but that percentage varies from year to year. Sometimes it varies significantly, but on average, it's about 35%. So some of the products, some of the changes that you'll see this year, a lot of people look at the products from the National Hurricane Center. Traditionally, their cone would show a storm approaching, and then just highlighting some of the warnings that come from the National Hurricane Center. So in this case, the tropical storm warnings and the hurricane warnings. Now we know that the impacts sometimes or quite often extend beyond the cone itself. So this year they are not only adding their own warnings, they're adding the warnings from their local weather offices as well. So some of the inland warnings are not really issued by the National Hurricane Center, but they will be included in the hurricane cone graphic this year, which really gives you a better representation of where the impacts are going to be. We're exploring what we do here in Canada as well, but this is something that they're trying this year at the National Hurricane Center to get more information on their products. Yeah, the website here, um, nhc.noaa.gov, will bring you to their website. And there's a wealth of information on there, whether the storm is approaching Canada or not, whether it's approaching the US, they will still have all this information on here. So a very good resource there. Um, there is one change in some of our approaches. One is with respect to coastal flooding. You might have seen on some of on our website and some of our other publications that we're changing the names of the type of warnings that we issue. At least in some jurisdictions here in Atlantic Canada, we're moving away from what we would call a storm surge warning, which is the hazard, to warn more about the impacts, and that is coastal flooding. So the storm surge causes the coastal flooding. So going forward, if we do have a hurricane coming up this year that would generate the risk of coastal flooding, we would have a coastal flooding warning as opposed to a storm surge warning. So this project is actually a national project, and we're looking at implementing the prediction and alerting for coastal flooding for all of our coastlines. Um, uh, so this is something that is new in a lot of areas here in Atlantic Canada. Is not quite so new because we've had it for a number of years, but it is new for some other areas. So some of the things that we can produce are things like coastal flooding risk maps, which is something like this that you might see on social media or some of our website or our weather app, which will outline the areas at highest risk for coastal flooding for a particular weather event. So that is new for this year. Again, to get um, the most out of our forecast, you can go to canada.ca/hurricanes. That brings you to the CHC website. We also have a couple of Twitter accounts, both English and French. And then, of course, all of our information is also on our um, our weather app as well. So with that, Glenn, I'll wrap it up and willing to take a few questions.
That's great, Bob. That's extremely interesting. And you took my short list of questions and already answered them, so I'm in a little bit of trouble there as far as questions go. But I just a note out to everybody on the line here. If you have a question, please pop it into the Q&A. And I'm going to start it off by asking, this question about climate change and hurricanes. And so, you know, we often simplify climate change and extremes and say, well, climate change means more of and worse of. And that's not necessarily true with North Atlantic hurricanes. We read a lot in the papers, and people just kind of throw out this blanket statement that, oh, we have more storms. And that's not really true. I don't think the data is really showing that we're seeing more hurricanes and not necessarily more intense hurricanes either. I think the jury is still out on that. So we have to really be careful about being super generalized really in that great degree. But there is some other inklings of some changes happening with hurricanes, namely, and you alluded to this, hurricanes forming quicker, hurricanes ramping up from basically Cat 1 to Cat whatever quicker, sometimes slower moving and oftentimes wetter. Can you comment on the state of the science in those areas and whether these things are starting to be confirmed, or are we still very far off from being able to make those conclusions?
Yeah, well, you're 100% right on. When it comes to hurricanes and climate change, it is not straightforward by any stretch of the imagination. We know that in a warmer climate, warmer air temperatures, warmer air can hold more moisture, more water vapor. So it goes to reason that some of these storms, especially if they start slowing down, or whenever they do slow down, there's more moisture contained in the storm itself. So a lot of that moisture, when it precipitates out, you're going to get some some very catastrophic inland flooding, and more rainfall, record rainfall with these storms compared to before, just because we're dealing with a warmer atmosphere. So that is pretty a safe statement to make. The other one refers to really what we're seeing with sea level rise. We're seeing sea level rise. That is pretty much, everybody understands that because we're getting into a warmer climate, that the poles are the ice caps are melting at a greater rate. It's the change in temperature. The warming is occurring faster at the poles than it is in the mid latitudes, and certainly in the tropics. So, and because of thermal expansion, you're getting a rise of water levels along our coasts. So that alone, even if the number of storms remains the same, you have larger areas that are now at risk of coastal flooding because of sea level rise, even if everything else stays the same. In terms of the rapid intensification, yeah, that's one thing that we're seeing, and there was actually a study done on this uh, um, that was released, I think, earlier. It was either late last hurricane season or in January or February of this year. That did show that a lot of these storms are going through, are experiencing that rapid intensification phase. More of them are going through this rapid intensification phase. Now, the caveat to that is that we are so much better at detecting these small changes within a hurricane than we were just 10 years ago, just because of some of the new technology that we have. So a lot of work is being done to try and normalize what we're seeing, because if we compare what we're seeing now to what we saw, say, 20 years ago, 25 years ago, it's so different that it's very hard to compare, because we're so much better at seeing the details of these storms and picking up on this rapid intensification than, say, we were a couple of decades ago. So if we're better at seeing them and we have the better technology to give us that detail, obviously we're going to be seeing more of it because we're better at seeing it. But does it really mean that it's happening more often, or that we're just better at seeing it? And there's a lot of statistical work that's being done to try and normalize that. So it's not an easy nut to crack, but if we look at some of the modeling for what we might see in a warmer climate, it shows that the total number of storms may not increase, but some of the ones that we do have might be a little bit stronger, and there might be more of them going through this rapid intensification.
Great. Thanks, Bob.
Yep.
Not straightforward, that's for sure. And we really have to
Yeah.
be careful about generalizing, I think, certain things. We have one question here. I'm not quite sure what it refers to, but the question is this alerting program an early warning system? I'm not sure which alerting program he's referring to, but
Um, Might be referring to the coastal flooding.
oh,
It's it it's certainly a new program overall nationally, if that's what the question is referring to. We did not have any kind of program for coastal flooding, either along the Great Lakes or on the West Coast, or certainly up north. And we have had a storm surge warning program here in Atlantic Canada since the Great Groundhog Day storm in 1976. That's what really was the catalyst to develop um, uh, a storm surge warning program. A model was developed in the early 2000s to actually model this stuff so we can get a pretty good idea of what some of these water levels might be, and then to document the water levels that cause flooding. So now in large parts of Atlantic Canada, we know which water levels are going to result in some degree of coastal flooding. And now we can look at some of these weather patterns 4 or 5 days ahead of time and get a pretty good idea of which areas along the coast might be at higher risk for flooding with a particular storm, if that was the gist of that question.
Thank you. Next question, with La Nina, are hurricanes less likely to curve, and I mean to ride up the Atlantic coast?
It depends on a number of other factors as well. It's not so much the La Nina that causes them to recurve. There are other things like the strength of the Bermuda High. So what typically happens is a storm will form in the tropical Atlantic. There is a huge area of high pressure to the north of it, with the air that flows around that area of high pressure um, being flowing in a clockwise fashion. So if the hurricane is down here and it follows the easterly trade winds, if that area of high pressure is weaker or shifts a little bit towards the east, that opens up an opportunity for that storm to recurve and come up either along the Atlantic coast of the US or potentially even up into Atlantic Canada, or potentially even uh, pass offshore where we may not see the impacts on land, but of course they would over our marine district. So that's something that we watch very closely as well.
Next question. Would it be safe to say that due to higher than normal Atlantic Ocean surface temps and the projected lessening of wind shear in the same region, along with warm air temps, that these traits are what are likely going to drive more storm creation, durability, and intensity?
Yeah,
So,
what happens when you see water temperatures with especially the pattern that we're seeing now? So we know that water temperatures are warmer in the Atlantic, in the tropical Atlantic, but some of those higher anomalies are actually further north into the subtropics. So what happens there is that reduces the overall pressure um, in that general area, and it weakens that Bermuda High. So what happens is that that water tends to, because those winds are lighter, the trade winds are lighter, the overall pressure in the area is lower, and that's a more favorable environment for these storms to develop. Also, because those trade winds are lighter, it allows the water to warm at a more rapid pace. So it kind of feeds both both things actually feed each other. The fact that the trade winds are lower, it allows the water to warm up faster, and that's what happened because we went from basically normal to slightly above average water temperatures in February, March last year to record water levels in the during the summer last year, and that was because of a weakening of those trade winds, and that is what caused the water, or at least a contributing factor to what caused the water to warm. So as that happens, that lowers the pressure in the area, and then it just causes more storms to develop, and it weakens the trade winds and creates a more favorable environment for these storms. So it's kind of a feedback mechanism going on there for sure.
fascinating. That's it for the questions from our guests, unless somebody else has anything. But Bob, after Fiona last year, any lessons learned, any changes made after that? Can you give us some thoughts on that?
Yeah, one of the biggest things that we've really done, and it wasn't necessarily a Fiona thing, but it was something that we decided a direction to go a couple of years ago well, I've been doing this for 20 years now, but is recognizing the importance of partnerships is absolutely critical. And the work that we're doing with our emergency management community, especially with respect to hurricanes, but not only hurricanes, but on winter storms, any kind of storm. For example, I have an office embedded within the Nova Scotia Emergency Management Office. The work that we've done with our emergency management communities across the country really has been probably the biggest change that I've seen in my career, and those relationships are critical whenever we're dealing with whether it's a hurricane or an ice storm or a flood. Those relationships are absolutely critical. And you mentioned at the outset the wildfires as well. Being embedded right within the emergency management office during the wildfires that we saw here in Nova Scotia last year was also very critical because you have that weather support right at your fingertips when you need it. So again, those relationships are probably the biggest change that I've seen in my career with Environment and Climate Change Canada.
Thanks for that. That's great. I think with that, we're going to wrap it up. Bob, thank you so much. Talking about partnerships, this is a long-held one, and we cherish it very much. Thank you so much. We know you're so busy, and we appreciate it greatly. Um, and to everybody on the line, this webinar will be posted probably Monday or Tuesday on our YouTube channel. The slides will be on our hopefully on our website. And join us next Friday again as our next Friday forum. We talk about roofing and siding. With that, take care, everybody. Thanks so much. Thanks again, Bob, and take care, everybody. Thank you.